everyone. So we left off at the end of lesson 2, and we're going to segue into lesson 3 today. So we're going to start talking about calorimetry first. So calorimetry is going to be a process by which we use a calorimeter, which is a device that's used to measure the amount of heat involved in a chemical reaction. Okay, in general, when we use a calorimeter in this class, we're going to be looking at like a coffee cup calorimeter. So this calorimeter is going to be designed to keep all of the heat inside of the reaction. It's going to make sure that no heat is lost to the surroundings. So we can measure really what's happening in the reaction just by a change in temperature, because we know that that heat is going to be transferred and it's going to change the temperature of my substance. And I can use that Q equals MC delta T equation to figure out how much energy was actually transferred here. So I'm using the idea that the heat lost by one substance will be equal to the heat gained by another substance, because I can't create or destroy energy, I can simply transfer it. So I have this transfer of energy happening, assuming that no energy is lost to the outside environment. How we generally see a calorimetry experiment is we take a cup of water and we put a piece of hot metal into that water. That hot metal is at a higher temperature, so energy is going to go from the metal to the water. Energy is going to be transferred from a higher temperature to a lower temperature. And I know that the amount of heat lost by the metal will be equal to the amount of heat gained by the water. And I can use two different Q equals MC delta T equations, one for the metal and one for the water, to figure out information about my system. So I can have a problem like this. This one says a 10-gram aluminum block at 100 degrees Celsius is placed in a calorimeter with 150 grams of water at 10 degrees Celsius. Heat transfer occurs until both substances are at 36 degrees Celsius. And that's what's going to happen in these calorimeters. The heat transfer process will happen until both substances are at the same temperature, and we call that a thermal equilibrium. So once both substances are at that temperature, they've reached thermal equilibrium, and the reaction's said to be over. So here they want me to calculate the specific heat of the aluminum. So I know everything that I need to know for my water in this problem. Okay, oh, I'm sorry about that. Okay, so let's look what I have for my water only. For my water only, I have this 150 grams of water, and I have its initial temperature of 10 degrees Celsius, and I have its final temperature of 36 degrees Celsius. So I can do a Q equals MC delta T specifically for my water, and I can calculate my Q here. So my Q, or my energy, is going to be my X. My mass of water was 150 grams. My specific heat, remember I get that from table B, it's 4.18. And my change in temperature, my final was 36, my initial was 10, so I changed by 26 degrees. So I can go ahead and calculate my X here. And when I plug that into my calculator, I should get 16,302. And remember, Q is measured in joules. So that tells me that the water gained 16,302 joules of heat energy. That means that my metal must have lost that amount of energy. So to figure out the specific heat of the metal, I can do another Q equals MC delta T for my metal, which is aluminum in this case. And I know that that Q is going to be whatever the Q was from my water. If it's gained by the water, it's lost by the metal. I know my mass of the metal was 10 grams. I'm trying to solve for the specific heat, so that's X. And my change in temperature, it went from 100 degrees Celsius to 36 degrees Celsius, so that's a change of 64 degrees Celsius. So again, I can solve for my X here. Okay, and this would come out to, say, I think it's 25.5. And then I look at my sig figs. Okay, 10 and 100. And 10 again, all only have one sig fig, so I want one sig fig in my answer, which means that this would give me 30 joules per gram degrees Celsius. Okay, so go ahead and try this problem. Okay, so we're going to do a very similar process here. Okay, first we're going to do a Q equals MC delta T for the water. So again, it's Q equals MC delta T. My Q, and again, this is for the water, sorry. So my Q is my X. My mass of my water, it says 20 grams of water. My C, my specific heat, I know from table B is 4.18. Then for my water, it says it's at 10 degrees Celsius, rises to 15 degrees Celsius, so that's a change of 5 degrees Celsius. I solve for my X. Should come out to 418 joules. Now I can do a Q equals MC delta T for my metal. And I know that all that heat energy gained by the water is what was lost by the metal. So that's going to be my Q here, my 418 joules for my metal. That's what's going to be lost. My mass of my metal is 5 grams. My specific heat is what I'm solving for. That's my X. And my change in temperature, it starts at 100. It ends at that same 15 as the water, because remember, both substances get to the same temperature. So that's a change of 85 degrees Celsius. So I solve for my X, and it should come out to, say, 0.98. Then I look at my numbers. That's 100 and 10. Again, only they have one sig fig here. So it should come out to 1 joule per gram degree Celsius. All right, so that's it on calorimetry. We're going to move into lesson 3 now, which is phase changes and heat accompanying my phase changes. So we're just going to do a quick review of solids, liquids, and gases, things that we did all the way at the beginning of the year that we should remember. So hopefully remember that solids have a definite shape and a definite volume. Okay, the particles, even though it doesn't look like they're moving, they are in constant motion. Okay, they would have to be at absolute 0 to not be moving. Remember, that's the point when all molecular motion stops. And since we don't actually ever reach absolute 0, we know that they are moving. They're just vibrating in place. Okay, the molecules are going to be packed tightly in this geometric or crystalline pattern. Liquids have no definite shape. They take the shape of whatever container we put them in, but they do have a definite volume. I can measure that volume of my liquid, and it doesn't change depending on the container that I put it in. They're in constant motion too, more motion than my solids are in. There's no real arrangement of particles. They're more scattered, and the molecules are further apart than in solids, but closer together than in gases. And my gases have no definite shape and no definite volume. They'll fill up any container that I put them into, and they'll take the shape of that container too. They're in constant motion. They're in actually very, very fast motion. They're most amount of motion of all of my states of matter. There's no arrangement at all of particles. They're completely scattered, and they're in general very, very, very far apart. Okay, so this is what my solids looks like. This is what my liquids look like, and this is what my gases look like. Okay, if we're talking about attraction between the particles, well, the closer my particles are, the more attracted they are to one another. Remember, we talked about these IMFs, these intermolecular forces of attraction, when we did our bonding unit. Okay, so solids are going to have the strongest attraction between particles. That means they have the strongest IMFs. Liquids have moderate forces of attraction. That means that they're moderate IMFs. And gases tend to have the weakest forces of attraction, so they have the weakest IMFs. So take a second and try to answer this question. Okay, hopefully we were all able to figure this one out. We know that aluminum is a solid at STP, and solids have definite shape and definite volume, so it should have been answer choice A. So when we're talking about phase changing, just some of the terminology that you need to know. When I'm going from a solid to a liquid, we know that's called melting, like an ice cube turning into liquid water. That's melting the ice cube. Liquid to a gas we can call evaporation, or we can call boiling. Okay, so we know if we put a pot of water on the stove, we turn the heat up, turns into a gas, we're boiling it, or those puddles outside going from liquid to gas, they're evaporating. Gas to liquid in the opposite direction now, that's called condensation. Liquid to solid is called freezing. Then solid directly to a gas, meaning no liquid phase, that's called sublimation. Like we know carbon dioxide, that dry ice, that solid carbon dioxide, that undergoes sublimation. We don't have any liquid phase happening there. And then in the opposite direction, that's called deposition. Remember, we saw this in the lab when we took those very small samples of iodine, those little purple crystals, and we put them in a test tube and we heated them, and that purple gas filled up the test tube. That was sublimation, and then we let it sit, and that redeposited on the sides of my test tube, and you saw the sparkly purple on the sides of your test tube. That was called deposition. So my phase changes can be endothermic or exothermic. Remember, endothermic means I'm adding heat energy. I have to add heat energy in, or heat energy is being absorbed. So melting would be an endothermic. You have to add heat to melt something. Boiling or evaporation or vaporization is also going to be endothermic. You have to add heat to make that happen. And sublimation is also endothermic. You have to add heat to make that happen. When we wanted our iodine crystals, those purple crystals, to turn into a gas, we had to put them into the Bunsen burner flame. That's adding heat energy. Phase changes can also be exothermic, so anything in the opposite direction is going to be exothermic. So freezing is exothermic. I have to take heat energy away to freeze something. If you want to take liquid water and turn it into ice, you have to put it into the freezer, which means you have to take away heat energy, turn that temperature way down. Condensation is also exothermic. I have to take away heat energy to make that happen. And deposition is also exothermic. So stop, take a second, and try to answer this one. Right, so hopefully we know when we want to boil water, we have to add heat energy, so that makes it an endothermic phase change. So what we're looking at here is a branch of chemistry called thermochemistry. When you think of thermo or thermal, you should think of heat. So this is the study of heat or energy changes that occur in a chemical reaction. Two types of energy we're really going to look at right now are kinetic energy and potential energy. Remember, kinetic energy is the energy of motion. Potential energy is stored energy, usually stored in my chemical bonds. And the big definition that I want to know for temperature, remember, is average kinetic energy. So temperature tends to tell me how fast my particles are moving. So if I'm looking at a phase change diagram, what this diagram is showing me, it's showing me at the bottom of my graph, I'm starting at a solid, and I'm adding heat or thermal energy to this solid. So we see as I add heat or thermal energy, the temperature of my substance, which is measured over here, starts to go up. Remember, temperature is also average kinetic energy, so I can also think of this as kinetic energy on the side. So as I add thermal energy to my solid, its kinetic energy, or its temperature, starts to go up. So along this first line segment here, I'm going to write Ke for kinetic energy. It starts increasing here. Okay, so potential energy then, if my kinetic energy is increasing, I can only change one type of energy at a time. I'm adding this thermal energy, and it's all being absorbed as kinetic energy. So that means my potential energy is remaining the same. And if I put a line over it, that just means it's remaining the same. So as I go up this first line right here, my kinetic energy is going up because my temperature is going up, but my potential is remaining the same. Then when I get to a certain temperature, you'll notice I end up with this flat line right here. This flat line represents a phase change. During a phase change, no temperature change happens. You'll see that here, that's why it's flat. You know that, say, water will freeze or melt at 0 degrees Celsius. The sample of water stays at that 0 degrees Celsius until the whole substance is melted, no matter how much heat energy I add. So that's why it's a flat line here. Now if this line is flat, that means kinetic energy is not changing because temperature is not changing. So all that energy, all that heat energy or thermal energy that I'm putting in is being absorbed as potential energy. So the potential energy is going up along those flat lines. Then once I reach this point over here, my whole substance has now been melted, so now I only have a liquid. Along this other line, I had both solid and liquid while I was melting. You know, if you put an ice cube on your counter, you see solid ice and you see liquid water at the same time. So you've got both of those phases happening at the same time. Once I get to my sample being completely melted, now I only have a liquid. So as I add more heat energy, the temperature is going to go up, which means the kinetic energy is going to go up. And that potential energy is going to remain the same again. But then once I get to this point right here, this would be the boiling point. Okay, so along this flat line right here, I'm going to be boiling. So I'll have both liquid and a gas here. And if my temperature is not changing, that means my kinetic energy is not changing. So all that heat energy that's being added is being added as potential energy. My potential energy is going up. Then once my whole substance is a gas, now I just keep increasing the temperature of that gas. So that's how we're going to read these phase change diagrams. So take a second and try to answer this question. Okay, so hopefully we were able to figure this one out. If we're looking at a phase change diagram here, okay, we know that I started a solid, temperature goes up, then I hit a flat line, that would be a phase change. Then a liquid, temperature goes up, a flat line, it's another phase change. And then the temperature goes up again. That's a general sketch of what a phase change diagram looks like here. So my phase changes are these flat lines. Okay, that means that temperature is not changing, so kinetic energy is not changing, but I'm still adding heat energy, so that means potential energy is increasing and kinetic staying the same. It should have been answer choice A. So if we look at one of these phase change diagrams for, say, water, we should see that first plateau being at 0 degrees Celsius, because that's the melting point of water, and that second plateau should be at 100 degrees Celsius, because that's the boiling point of water. So that's the end of lesson 3. We'll finish up with lesson 4 later in the week, and then we'll be done with this unit.